Welcome to the Structural Engineering Podcast. You may recognize this name from our last episode.
I'm Jordan Jarrett.
When we were talking with Jordan, we started discussing a building type that we have never designed, very few of us ever have or ever will, and we were so excited about it.
Talking about tall buildings today.
There aren't that many engineers that get to work on high-rise in their career, but I don't know if there's a single one that doesn't want to learn about it. The systems they use, in what ways they're different from a typical 1, 2, 3-story office building. Luckily for us, Jordan was willing to have another conversation and let us get every question we had about these super tall towers out. So please enjoy one more conversation with Jordan and learn a little bit with us about super tall tower design.
I worked as a structural engineer in Seattle for about 7 years and was able to work on a number of tall buildings across the country, both in high seismic regions and high wind regions. So I had projects in Seattle and San Francisco. Those were my high seismic regions. Those got up to about, I think, 600 feet. So I worked on Park Tower in San Francisco, which was 605 feet,
Wow.
and then a tower on the Amazon campus, which was 520 feet. So those are my tall buildings in high seismic regions, and then worked on a handful of tall buildings in wind regions, so Miami and Chicago primarily. So my big Chicago project was 150 North Riverside. I was one of many engineers that worked on that.
Quick note, talking with Jordan after the show, she realized the height of 150 North Riverside was 724 feet tall, so I wanted to edit that detail. Just to keep a physical scale to such a large number, that is also 0.6 Empire State Buildings, or 2.4 Statue of Liberties.
And if you haven't seen it yet or seen a picture, it's built on a really small piece of land. There's a river on one side and railroad tracks on the other. So the footprint of the building gets very small at the base, and then via a large transfer truss, I believe it's 4 stories tall, the footprint gets much wider so that it's an actual usable size for office. And then I also worked on a project that has unfortunately died, so it will not be built, but Skyrise Miami, then that was 990 feet. So we almost hit the 1,000 mark, and that was going to be an observation tower entertainment space, but it did not survive the pandemic. So, but it was a cool project to work on. So those are my experiences, tall structures in a variety of different climates.
That's very cool. I'm restraining myself from interjecting with silly questions, but they will come soon. So I'll start with thank you very much for joining us again, Jordan. We've heard and know that you have experience with tall buildings, and that is a topic that really interests Zach and I. So we wanted to just lay out some general questions for you and pick your brain a little bit. And I guess
great.
I'm going to start on a very simple one, just because I use the skyscraper, those words often, and it feels like words from a Superman movie or something. Is there like an in-office correct term? When you say, if you tell someone in an elevator you work on skyscrapers, that seems a bit weird. What's like the category?
Yeah, we typically say high rise, right? We often will categorize buildings into low rise, mid rise, and high rise. So that's the first one. But those are pretty vague, right? What exactly does that mean? I think it's probably firm specific, honestly. So tall buildings, I think, is the correct term, if you will. CTBUH, the Council on Tall Buildings and Urban Habitat, have a little bit more information on this, mostly varying levels of tall. So there's like tall, super tall, and I think the third is mega tall. And they have very distinct cutoffs for the super talls and mega talls. But even they say tall is kind of subjective, right? A tall building in San Francisco is very different than a tall building in a rural or a suburban area. But I think that's generally what I hear is they're described as tall buildings. But I do like skyscrapers, right? That's kind of a fun term.
Well, we'll try to use the word tall building, but I have a feeling that we're going to defer to skyscraper a lot.
So a big drive for the podcast is to really influence and teach young engineers. So, what would you say to a young student that was really interested in doing skyscrapers, tall buildings? What is the odds of that happens for them? And then what could they do to maybe increase that?
Absolutely. I think the odds of it happening aren't great, aren't very high if you're not proactive. And I think it's just the number of buildings in our country and the world that are tall buildings, right? And I've heard the number before, but it's something really small, like less than it's definitely less than 10%, but maybe even less than 5% of the buildings that we as structural engineers design end up being classified as these tall buildings. So if you were interested, there's a few things that I would recommend. The first, and I'm sorry to say this, Zach, but go get your master's for sure. There's very few firms, I think, that are going to be specializing in high rise that have master's preferred job openings. Preferably get a master's at a school that has a heavy focus on lateral loads, lateral systems, because that's really what takes more effort, right? What distinguishes high rise from mid rise is our lateral systems often. So if you have a school that really doesn't teach about seismic design or wind loads, it's not going to set you up very well for joining a firm that specializes in high rise. And then just figure out what those firms are. Go to, as I mentioned, the CTBUH, their website. They have a list of the tallest buildings, right? Top 100. I'm sure they have more. And just see what firms are designing these tall buildings and, try to get internships there, try and network as early as you possibly can, get your foot in the door. And then be prepared to move to a big city, right? You're very unlikely going to be designing these if you want to stay in a smaller city or in more suburban or rural locations. So you're probably going to end up on the West Coast or Chicago or, the New England area. So if you're okay with that, then there's certainly the opportunities. But even if you get into a company that designs high rise, that's usually not all they do. So being proactive in your desires can go a long way.
How many structural engineers does it take to design a high rise? I think you had mentioned before that you were part of a larger group. Like how could we compare this to a typical, 3-story office building? Might take a couple, one person primary and then a few stragglers. How would a high rise function generally?
Absolutely. So it obviously depends on how fast the schedule is. Faster the schedule, the more people you need to work on it. But I would say for a normal paced schedule, you're typically going to have obviously your principal and your project manager, and usually they're going to help with some of the really complex technical aspects, which maybe isn't what happens on smaller buildings. And then usually 1 to 2 people focusing on the lateral system. It kind of depends if it's high seismic or if it's wind. If it's high seismic, now we're going into performance-based design territory, which takes a little bit longer. There's more pieces to it. So maybe let's say there's one person that builds the model because it's quite a bit more advanced than a typical linear model. And then there's maybe one person or two who are doing the design because there's a significant amount, particularly you have to add in all the work with the diaphragms and the lateral system and the foundation. So maybe 2 to 3 on the lateral system and then probably 1 to 2 on the gravity system, depending on how repetitive the design is. A lot of these tall structures, the gravity design's not that much more complex because you get some very repetitive floors. So if you have a 73-story structure, you might only have, 15 unique floors, and that's pretty comparable to a mid-rise. Obviously, the load rundown, your columns are bigger, your foundations are bigger, but sometimes if there's common themes running through, the gravity design isn't as complicated as it might seem.
You brought up performance-based design. Could you discuss what that is a little bit, and then also talk, is that what skyscrapers always utilize as a design system? And then at what height would you enter that realm of performance-based design?
Absolutely. So performance-based design is essentially going outside the code and showing that even though your building does not satisfy all the requirements of the code, it does meet the intent of the code, right? It meets the reliability that is assumed, the safety that's assumed. To do that, you need to do more thorough analysis. You're going to have a peer review so that somebody external can essentially agree with you that you are meeting the intent of the code. And usually when we talk about performance-based design, we talk about performance-based seismic design, so in high seismic areas. And I think that's what you were alluding to with the height. So in ASC 7, based on your seismic design category and the lateral system that you use, there are height limits. And if you exceed these height limits, that's when you're going to have to go to a performance-based design. So for example, in seismic design category F as in Frank, you can find some systems that go up to 100 feet. And if you meet some certain criteria, you can go up to 160 feet. But that's about the limit. Anything more than that, you're almost certainly going to have to go to your performance-based seismic design. In design categories D and E, you get a little bit more, right? You have quite a few lateral systems that can get you up to 160 feet. And then again, if those systems meet certain criteria, that can be bumped up to 240. So those are kind of the limits, right? 100 feet, 160 feet, 240 feet. And if you want to build higher than that, that's when you're going to go to our performance-based seismic design. And again, it requires a peer review, so an external firm with similar levels of expertise in this seismic design. It requires a nonlinear analysis model. So usually we just build a linear model and do our linear analysis, right? ELF for modal response spectrum analysis. When you go to PBD, now you actually have to model the nonlinearity that we know happens in earthquakes, but it's kind of a pain. So most engineers don't want to do that. But if you do go outside the limits of the code, you're going to have to do that more robust analysis model. And then you actually develop earthquake time histories with a geotechnical engineer and apply those to the model. So now you're actually shaking these models under realistic earthquakes, or as realistic as we can get given the amount of data that we have from historical earthquakes. But yeah, so a little bit more involved of a process, but at the end of the day, you're still meeting the intent of the code.
So you told us, your intro about the tall buildings you did, and let's just use 150 North Riverside. That was just over 700 feet tall. In the code, you still have to have a seismic system. And so maybe it's not necessarily governed by it, but are you still designing for performance-based seismic systems when you're in a wind-governed region but super tall?
So in that case, no, right? We're going to be designing, we'll check seismic loads, right? The kind of this idea of notional loads, usually 1% of the building weight. If we apply that, does that ever exceed the wind loads? The answer is generally no in Chicago. But in these lower seismic design categories, so B and C, there's a lot of our lateral systems that have no limit on height. And so there's no concern that way when it comes to wind-governed regions. We don't have to go to a performance-based design. But performance-based wind design is actually something that's really new in the past 3 or 4 years. Is starting to gain traction. I think one of the very first projects that was designed under the performance-based wind design is now under construction or just completed. So that's brand new. So we are getting into this idea of why don't we take some of the lessons learned when we did this performance-based seismic design and then apply it to these wind regions. And it doesn't work for every building, but there's a lot of buildings that can benefit from doing a more robust analysis and really being able to reduce these systems. So the answer by code, no, there's no requirement to do performance-based design for wind-governed buildings, but there is now that option that, again, is very brand new within the past few years.
Awesome. Yeah, these next two kind of questions I have, I don't know if they're questions or comments or thoughts on. I'm curious your reaction on them. So
yeah.
doing research on building height limitations, I think, is always intrigued me, and I've been always very interested in where did these height limits come from. And reading the California's Blue Book states that it's an arbitrary number that they drove around after earthquakes and said, well, that building stood up. It was this tall. It was this system. Let's govern it by that. But even before that, the city of LA limited, I think it was the 160 or maybe the 240 feet, just because they didn't want buildings to be taller than that. Do you think that we should look into those height limitations more or change those to be more of a based on, actual data and testing, or should we keep it to kind of how it is, which appears to be more of a gut feel?
I think we absolutely should revisit the height limits. They were for sure a gut feel. A lot of the code is, but they're arbitrary. The old wives' tale that I heard, and take this with a grain of salt because I have nothing to actually back this up, but that there was a sun study done in, I believe, somewhere else in California, maybe San Francisco, and they wanted to make sure the buildings didn't get too tall where the sun would be blocking parks and other things like that. And so they set a limit, and that was the only thing that LA could find when they were looking to set a limit, and started with that. But there was a typo in San Francisco as 150 feet, and someone accidentally wrote it down as 160, and that's where we get it. Again, old wives' tale, who knows if it's actually true, but it goes to these were arbitrary. There's not some science and analysis with it. It was put in the code a long time ago, so they didn't have these really thorough analysis programs. So I do understand, but yes, I think they are outdated. I don't think they're anything more than historical at this point, and we certainly could revisit those and make them a little bit more based in science and current knowledge.
Yeah, I was talking with a professor that did the research on CLT shear walls, and I asked him, why did you guys limit that to 65 feet? You kind of just match what wood shear walls could do. And he goes, yeah, it's really hard to push that through to get people to change their thoughts on the height limitations. It was already set as a precedence, so we just went with it and everyone accepted it. And now they're doing, research on tall mass timber and CLT systems. So I'm sure we'll see that changing.
Exactly. It's we definitely could update it, but with these performance-based design options where there is at least the opportunity to build taller. So it might seem to many as it's good if you're going to build a tall building to do these extra analysis. So we should just keep letting people do these extra analysis and really understand the behavior of their buildings fully. So I don't expect the height limits to change anytime, but they certainly could. I don't think they're based on anything more than just history and typos and things like that.
Do you think with AI technology and performance-based design, do you think we'll see that performance-based design becomes a little more readily available for more designers?
Great question. The answer is probably yes. I would say the thing that took the longest, or was, let's say, hindered our progress the most, was actually computing power. These analyses could take days to run. I think some of our projects took 2 weeks to run a set of analyses, and then you get peer review comments back and you do it again. So those were often the hardest part. So, which I don't necessarily think is going to be helped with AI, but building the model quicker, right? You have a lot of repetitive elements that you put into models. If you can start to build those much faster. Actually, one of my colleagues, we were using Perform 3D at the time. That was the software program. And it's a lot of just repetitive clicking. And he programmed if it was VBA or something else, to do the clicking and input the information correctly. So presumably with AI, you could also do something like that, potentially building ground motion records a little bit more readily could also speed up the process. But the computation power is what really slows it down. So
awesome. Yeah, this last one, that I wanted to add, it's just on my mind when you brought up ELF or versus modal response analysis. I was just watching a webinar the other day through FEMA, and I think it was like their their P 2012 study or something like that, and they determined that the ELF response is and loads that you get is so much more well enveloped than modal response analysis. Any thoughts on that at all? It blew my mind because I always thought modal response would have been the better route to go, but they did a bunch of studies and are now suggesting almost not using it.
Interesting. Yeah, when I was in
Okay.
my PhD, we were seeing kind of the exact opposite. We assumed modal was more robust, and I mean, I guess the thing is, I'm guessing ELF is more conservative, right? Because you're
Yeah.
not actually taking into account any higher mode effects, things of that nature. Because there's been a lot of work to make ELF less interesting or less appealing. There used to be a reduction factor, so that's been removed from the code. And now with our software technology,
Yeah.
applying the modal forces is negligible, right, in computational power. So there was a pretty big push. So that's interesting to hear. I hadn't heard that, and I honestly I don't know. I don't know what the history is. Maybe we go to linear time history analysis, which I know is one of the options, but I don't know how often that one's used given the added burden of developing time histories.
So I'm going to swing back to wind real quick and sort of wind tunnel testing or computational testing. So do all skyscrapers, tall buildings require that level of wind evaluation? I've heard that will often produce a lower wind force on a structure. At what point does that become necessary? Does it ever? How does that work?
To my knowledge, there isn't a requirement, but yes, typically wind tunnel is done to be more accurate, and often does reduce the loads. Although I have seen some projects like in Miami where the loads were actually higher for the wind tunnel. They're more accurate, so it's worth designing for them. But there is the chance that you're not actually going to get a lower force doing wind tunnel. I don't know exactly what the cutoff might be, but pretty much all of the projects that I worked on had a wind tunnel done if they were in a wind region. Even, there were a lot of projects adjacent to me that were probably in the 15, 20 story, and a lot of them were doing wind tunnels as well. So I think it's pretty common in high rise just to get the most accurate loads on there.
So we kind of talked about like how big the project team is. What would you say is the duration to design a tall building?
Again, it depends on if it's got peer review, right? So anything that's doing performance-based design, whether it's seismic or wind, you're going to add time for that peer review process. So for the two PBD, so performance-based design projects for seismic, I think that whole peer review process took about 9 to 12 months. And you can do a lot of overlap, right? Somebody can be designing the gravity system while you're looking at the lateral system for the most part, but that tends to add some time to it. Otherwise, if it's a little bit simpler, if the gravity system's repetitive, I think that the times are often not as different from mid-rise buildings as one might expect. But in my experience, it's all owner-driven. Some of our projects have really long timelines. Some of them have really short timelines. And then it's just making sure that the scope of the design fits in with the client needs. And it's just that peer review process that you really got to account for that time because there is that back and forth. There's the long analysis run times. And so that often can't be hurried too much or accelerated too much.
That makes a lot of sense. A question that popped in my brain that I'm not sure how to necessarily phrase or ask, but I'll give a little bit of a backstory to it and see where it goes. Max's background, he worked on a lot of low-rise buildings, kind of the turnover of designing those or maybe a 3-month, 12-week period. He then moved to a firm where he was doing 12 to 20 plus story towers, and that design time really extended out. My question comes to be, do you think that working on tall buildings with probably a lot, maybe longer schedule it keeps people less interested? I'm not sure how I'm trying to phrase this, but do people get bored? Do you get bored because you're doing the same thing repetitively once things are built versus like if you're doing smaller projects more often? Do you have any, I guess, thoughts on that?
Absolutely. I think, as a young engineer, you should want to experience a lot of different projects. Even if there's similar projects, you work with new people and new teams, and just building that set of skills, both technical and communication, is really beneficial in the first few years. And I think there's that opportunity on high-rise projects as well. As in, you might not be the same engineer start to finish on a high-rise project. Very often I would see projects where someone comes in and does early design through, I don't know, 50% CD, let's say, and then gets moved to another project, and another engineer comes in and finishes the design and does CA or things like that. So I think there are opportunities if your firm wants to give you those various experiences. But yeah, you're going to have to move around more, and you might not see a project start to finish, which can also maybe be something that you want to do, right? You want to have that entire scope of experience. So absolutely. You can definitely get pretty repetitive, especially in the CA phase, right? When we're talking about a steel building that's 40 stories tall, you look at a lot of steel shop drawings. And if it's one person doing it, it can get very repetitive. So I think if you're working on tall buildings, you just need to be at a company that's mindful of that and tries to make sure that you get that variety of experiences and aren't stuck doing the exact same thing for, a year or two. You could get pigeonholed doing things in a small building too, right? You design the core walls for every building for the next 3 years. Equal concern, right, of just doing
Absolutely.
the same thing. So yeah, hopefully your firm is proactive in giving you a variety of experiences.
Yeah. Now I never really was thinking about construction, but now you got me thinking. The shop drawings are probably immense. But when it comes to going out on site and seeing the building, how often are you doing that? Let's say, with the 70-story tower, what is the frequency of that? Because when we're talking low rise, it's maybe 1 or 2 trips to see the building, but for a big building, is it similar?
I think it's going to be more often. We would typically try to be out there anytime there was something new. So there, obviously foundations are a huge one. Your first above grade installation, whether it's steel or a concrete pour. You want to see the first few levels of the shear wall being built or the brace frames being built. So earlier on in the project, there tended to be a little bit more. And again, it was just trying to be there for the firsts. And then as it progressed and things were a bit more repetitive from both the structural design and the process for installing it, right, the construction process, be a little bit less frequent. I would say, unless there was a problem, going out every other month or so might be pretty normal after you get through those first set of firsts, if you will, which tended to be a little bit more regular. Now, we had some projects that were not necessarily high rise. These tended to be the long span, but we had some projects where an engineer would go move to the city and be on site basically every day because the project was just so complex. Everything was unique, right? Everything was a first, and it was something that the owner really wanted in the construction phase. So a bit owner directed, a bit, how involved is the inspection, the city inspector coming regularly, and then just how often do we want to make sure things are going as planned. But after the bigs, the firsts, it became a lot less frequently required.
Since you mentioned CA and the construction phase, it kind of popped in my head. There aren't that many firms that can take on a tall building, structural firms, right? It's, who knows, but maybe 1% really. Is there a section of construction companies that also will take on these tall buildings, like a small group that you work with them in the past, mentally can kind of list off who's doing this construction?
I think it's pretty similar. Same with architects too, right? We tended to have a lot of similar teams, right? Both the architects, the engineers, the contractors. There did tend to be groups of each subset that were more set up to do tall buildings. So yeah, I do think on all sides of the phase there are firms that specialize in high rise. And then the majority of firms likely don't want to get involved with the process.
Yeah, it's got to be a very unique group to enter into, really.
Yeah.
I was curious, what specific education? Now, you've already talked about, you recommend a master's, but what other education do you think people should focus on to design tall buildings? Like, should they lean PhD if they really want to be in that space, or is it more of a spectrum?
I would say no, you don't have to get a PhD to get into tall buildings. And honestly, and I think we talked about this a little bit on the last podcast, but having a PhD was a little bit of a hindrance in job searching, even with these firms that wanted or that design high-rise structures. So it's not the norm to have a PhD. There certainly are plenty of PhDs who are working in industry, working with firms, especially on the heavy analysis side, right? Building those analysis models, running these high-end analyses. But it's definitely not required or kind of the norm or the assumed, at least in my experience. I would say the best thing, again, is where you pick your grad school and make sure you're learning as much as you can about lateral loads, lateral systems, foundations, right? The things that are really heavily impacted by these large structures. And if you're getting a master's and heading to the West Coast or the Northeast corner, right, that might just help you with the networking as well. But just making sure you get as many classes as you can on the lateral loads and systems is great. But yeah, most people don't need a PhD to work at a firm that specializes in high rise.
I'd say that's good. That's good to hear. So I was thinking, while we were thinking about, what to talk about and questions for you, it's popped in my head is, did you learn anything about skyscrapers that really surprised you when you were looking into the design?
Yeah, I think so in the design side, the thing that stood out to me is how much really coordination we should be doing, particularly with the contractor, the MEP systems, because our stuff just gets a lot more congested, right? Our core wall, the rebar in our core walls gets a lot more congested. And if we're not being proactive, it's harder to build, right? If the contractor doesn't understand what the requirements are or what we're designing, if we're not providing enough pathways for all the MEP equipment to go through, it just makes that, again, construction administration phase really time consuming and you run into a lot of conflicts. And so I think that was one of the things that I hadn't necessarily thought about. It was like, oh, you just put in more rebar, it's fine. Well, it's like, well, no, you put in more rebar, but can the contractor actually build it? And can the MEP system still have enough movement, be able to get through your core wall? So that was one thing I think having those conversations early was really helpful when kind of thinking about the design. And then I would say maybe less on the design part, but sort of what surprised me about high rise was my favorite projects were not necessarily the coolest and the tallest. It's fun to be able to go to a city and be like, hey, I helped design that. But absolutely my favorite projects were the one where the team was the most enjoyable to work with, right? Where we had a really good relationship, where we worked well together, whether it was internal and external. But absolutely, the people were a lot more important than the projects to me. And I kind of use that sometimes with my students. And going back to your early question about, how do you make sure students, or what can students do to position themselves to design high rises? I think that's an admirable goal. But I also think it's worth recognizing that the coolest project in the world will not be very much fun to work on if you're working with a team that you just don't want to work with, right? For whatever reason, you're not getting along, you're not supportive, you're kind of conflicting with each other. So I think that was actually one of the things that surprised me about high rise is the cool projects weren't necessarily the best projects for me. It's just simply how the team goes and how everything else goes. So as students particularly, or if they're finding it challenging to break into the world of high rise, I can guarantee you could find a place where you're going to enjoy your work if you're with a team that supports you and values you and works well together. So it's a
Yeah,
little
so
bit of a tangent, I think, but that was probably one of my biggest surprises.
I really like that. So yeah, thinking about teams and like getting to interact and stuff, on from my experience, and I think Max as well with working on low-rise buildings, a lot of the time, the principal in charge, project manager, sure they have, they're talking with the client and the architect a bit too, but often the design engineers and the people on the team are interacting with the architect and their staff and their team. On a skyscraper, is it the same way? Were you interacting with the architect quite frequently?
Absolutely. And my first year or two, no, right? I mean, the first year or two, you're pretty much working with your project manager, and they're the ones who are coordinating with the architect. But as I got more advanced and a little bit more autonomous in my design, I would do that coordination with the architect. And then on my CA projects, right, you're constantly in contact with the contractors and the architects. So I think it's one of the best things you can do as a young engineer is actually try to get into more of these coordination meetings, see why things are being built the way they are, and build those communication skills, right? And we've talked a lot about this between these two podcasts, but those communication skills are as important as the technical skills. So if you can get in those rooms, even if you're not necessarily contributing at first, right, you're just kind of listening and learning, I think it's important to be on those calls or in those meetings if you can be, because pretty soon you're going to have 3 years worth of experience. You know what you're doing on the design side for the most part. So there's no reason that your project manager needs to do the coordination and then tell you what to do. You can kind of streamline that process, and it's a good thing to do. It's a good thing to know why you're designing what you're designing. But I think that's pretty similar, whether you're high rise or low rise. I think the teams get bigger, so you might not be talking to all of the architects and all of the contractors, whereas maybe on the smaller projects you are, right? Everybody involved. But we're definitely pretty involved with the whole team. Once you have a little bit of that, again, autonomy to do the design without as much oversight.
Yeah, and probably some coordination with those mechanical engineers, those pesky mechanical engineers. I want to poke holes in all of our structures, right?
All of our structures. I know
I don't know why a shear wall is
it's
attractive
fine.
to them to pop a hole
They
in.
do.
I don't get it, but whatever.
Yeah, they always want to put holes in the exact spot where they shouldn't.
Always. So tell me about the lateral systems. As we're going up in height, what is the typical thing we see?
Like for the tall buildings?
Yeah, for the tall buildings.
So all of my designs were concrete shear walls, and those are going to be even more, I don't even know if more common is the right word, but they recently added a new structural system to ASC 7 called a coupled shear wall, which gives it a higher R value, which just means it's better at high seismicity, right? And previously, they had an R of 5 or 6, depending on if you thought it was a bearing wall or not. And now you can get an R of 8, which matches buckling restrained brace frames. So those two, I think, are usually where we start. We usually start at core walls or BRBs. And in my experience, I did all core walls. So core walls or shear walls are nice because they're often in the middle of the building, right? You can build a wall around your elevators and your stairs and your back of house stuff, all your MEP stuff. And so they're away from a lot of the occupied space, which is nice. I think some architects really enjoy the look of BRBs, and I love it. The more we can show off our structure, the better. So I'm always a big fan when architects want to put big braces on the perimeter. I think that's amazing as a structural engineer. But it just depends on the building, on the architectural preference. My experience was all concrete shear walls.
So give us a reference point on maybe relative thickness of these walls towards the base and strength.
Oh, yeah.
I'm imagining they get very thick and very strong.
Yeah, I think we had, it was very common to get up to 10 KSI concrete. And I think we had some If I remember, we had some that were pushing like 12 or 14 if we could get it. Now, you can't use that in all aspects of the design, right? ACI limits sometimes the amount of concrete strength you can use in portions of the design, but we could still use it in others. And it's really dependent on if you can actually achieve that. Various jurisdictions just don't have the aggregate that can achieve 12, 14 KSI concrete. But when we were in a place that did have that capabilities, sometimes we pushed it pretty high. I don't know if we ever actually were able to specify 14, but I think we might have tried once or twice, at least on my projects. I easily had wall thicknesses that were 48 to 60 inches for some of these projects. So they could get pretty thick, and then just more walls depending on how long they were and where they were located.
Were you guys doing high strength bar as well?
Oh yeah, absolutely.
Yeah.
And there's rebar is getting into the 100 KSI realm. Again, you can't use it everywhere, but there are applications, which is ahead of structural steel, which is disappointing for structural steel. I think we need to catch up. Rebar side has figured out 100 KSA. Hopefully the steel side can figure it out soon. But yeah, we were looking into high strength steel absolutely in the rebar, and honestly in our gravity columns as well. Again, we're not at 100 KSI, but that's a pretty common way to account for this, since there's a lot of load and only so many rolled shapes. Going to that higher strength steel is a common application these days.
I've taken part in the design of an 11-story structure, and that's the highest that I've really been involved with. And we were really high on the steel size list of it. And we had kind of weird seismic conditions. This is the corner of a brace frame, so it was having a percentage from both. But we're still quite high on that list. Is there, if you're doing a super tall structure, are you doing custom built shapes or higher strength steel often, or does the gravity system tend to be okay with general rolled shapes?
So the gravity system, we still need something more than just our typical, I think W14 by 730 is the tallest W14. So we find that we do exceed that pretty regularly at the lower levels. So absolutely, high strength steel, 65 KSI is really common. I think we're even pushing closer to 80 KSI. I don't know that that's as common yet, but definitely working towards those higher strength steels. We'll often do something built up, so either add side plates. Occasionally we'll do concrete encased columns, so we'll actually combine and use the composite system. But there are more jumbo shapes as well, so the steel shapes are getting a bit bigger, which is helpful to us, assuming that, right, you can procure these big shapes because only a few fabricators are going to make them. For example, on 150 North Riverside, the over 700 feet in Chicago, that one was extra unique because of the small footprint. So we had a lot of load going into only a handful of elements at the base of the structure. So the columns that ended up going all the way to the base, I think the largest one we had was 2 of the W36 by 925, which at the time was the largest shape available. It might still be the largest shape available, but we put 2 of them together, and I'm almost positive they were also 65 KSI. So yeah, now again, that's the extreme because we funneled a lot of load into those columns, but we have seen some pretty robust columns for sure. But side plating is really common. That's usually our first step, right? Can we just add some side plates when we're in a basement, right? Concrete encased works great anyways because usually our below ground infrastructure is concrete already. So things like that. But yeah, the jumbo shapes are also pretty exciting if you can get them.
We talked about, BRBs and shear walls and stuff, but at what point are we kind of going beyond the capabilities of those, or maybe the capabilities of what the foundation system can do, and we're using outriggers or something else, maybe something else complicated to manage those forces? What do you typically see?
That's a really interesting question, and it's gonna be primarily architecturally governed. I can probably design a core wall for pretty much anything if the architectural would allow me to. And as we know, that's not always possible, right? There's limits on how far our structure can reach. So particularly if you have a aspect ratio where you're really wide in one direction and really short in the other, and so you have a thin core wall, that's going to tend more to requiring outriggers or something like that than a pretty square core wall. Near site effects can also affect that, right? If you're right on a fault and you have a significant directionality in how your earthquake would hit your structure, occasionally, right, that's going to affect your system and require something more than what you would normally do if you were away from the fault. So yeah, it's gonna be primarily architectural based. I know Salesforce Tower in San Francisco, it's over 1,000 feet tall, and it has no outriggers, no dampers, anything. It's just the core wall and a really robust foundation system, right? They had to work very hard to get the correct foundation for the core wall only system, but they were able to do it. And it was a desire of the owner, is my understanding. And so the team, the architectural team, the structural team made that work. So it's definitely possible. I don't think there's necessarily a very specific limit, but it really comes down to how the architecture of your building works, and if you need those outriggers, those dampers, etc., to just make sure that you can fit enough structure where you're architecturally allowed to.
Okay. Now, kind of thinking back to CA a little bit, and now, you said about concrete shear walls. During construction, how are you reiterating models as concrete strength changes, as it's proportionate to the stiffness? I mean, what is occurring? I'm just thinking, man, these towers are super tall. That concrete strength, thus stiffness, really probably needs to be dialed in. So how much robustness is there in the design for that, and how much are you validating or verifying that during construction?
It's actually a really interesting question. We're definitely keeping an eye on it, and the analyses, the nonlinear analyses, account for assuming that it's all a little bit higher than specified, right? There are factors that we put on our concrete strength, our steel strength, knowing that we're almost never just right there. We're usually going to be a little bit higher. So we did take that into consideration to some extent. It's rare to go back and totally redo the analysis. But with performance-based design, we really are modeling such a robust model. There are a lot of times that we're having to tell contractors, no, you can't increase the concrete strength. You can't add more rebar. You can't whatever, because of how thorough our analysis was originally. Deviating too much from that would, quite frankly, kind of violate the peer review. So those are some interesting conversations where a lot of contractors are like, oh, well, we're just going to upsize something. That's no big deal. And sometimes with PBD, it is. And we have to have those conversations. So I would say that's more common, just kind of working with contractors to find the right solution to their means and methods. We're obviously not doing means and methods, but kind of helping them with the constraints that we need to keep them in. But yeah, it's definitely something we have to be more concerned about from the PBD process primarily. So similarly with like steel columns or concrete cores, we monitor where they are elevation, because as you put that much load on them, you're going to compress them. And so we want to make sure that all of our structure is where we expect it to be. So there's usually a pretty thorough monitoring process, particularly on steel columns. And if they're not where we expect them to be, we might add some shim plates to make sure that they kind of stay where they need to be, and make sure that there's no issues with differential elevations that are unexpected.
We had a pause here since I had to step away, but now that I'm editing, I wanted to add the ACI concrete and steel strength limits. Now these are not cut and dry, but generally the highest allowable steel strength is 100 KSI, and the highest concrete strength that you may typically see is 8 to 10 KSI. SK Gosh has a great article on both of these and mentions this concrete range is now considered routine for high seismic tall building applications. Okay, now back to the episode for a few more questions.
What percentage of tall buildings use damping systems? And besides maybe a mass tuned damper, what other systems are being used?
In my experience, I didn't have any systems that used dampers for seismic, but we did use dampers on wind structures, and it was to control our serviceability level accelerations for occupant comfort, right? We didn't want people feeling seasick while they were at work or at home. So those, in my experience, are what I've used. And I think they're honestly going to be pretty varied just based on jurisdiction, right? Who uses dampers frequently? Who what architect has the right information and likes to include them in the designs. I know of some in like stadiums and things like that, but in my experience in the high rise, the first step would be outriggers if we needed something a little bit more. It wasn't commonly the dampers. It's a very
That's so
different
cool.
approach.
Tell me about the foundation systems for tall buildings. I'm assuming maybe we got some high uplift from overturning from the lateral system. How do we handle that? What's kind of most common?
Absolutely. They're big foundations. In Seattle, primarily we had just huge mat foundations. And these, I should look up what the thickest one I worked on, but at least 12, 15 feet deep. Person can stand in between all the rebar. Right? That's like the fun picture that you can get that for. So huge mat foundations. Absolutely, you're dealing with quite a lot of uplift. So you're designing these for that. So you have this huge mass of concrete essentially to help contradict that uplift. And it's just based on the fact that there's good glacial soil in Seattle, so you can do that. In other places, Chicago, and I know Salesforce Tower, talking really deep foundations and lots of them, right? Just tons of piles down to bedrock, and just put as many piles as you need and you can fit under the footprint of the building. And if those aren't enough, then there's certainly a conversation to be had with the architect or contractor. But those are what I typically see is very deep piles to bedrock or just massive mat foundations. So I don't know if they tend to be that much different than normal foundations. They're just much, much bigger. I think Salesforce maybe being the unique one there. I know they had a pretty intricate and groundbreaking, no pun intended, but groundbreaking foundation there. So sometimes you're certainly going to have to adapt for some of these tall buildings.
Yeah, I've seen some really interesting new design techniques for foundations. It's like almost their performance-based soil interaction stuff. I mean, it is crazy.
It's a little ironic, right? When we're, as engineers, we model this incredibly complicated building, but often our supports are just pins. Maybe springs, but maybe just pins. And then on the other side, the geotech has this incredible model of the soil, and then the building is just the single degree of like maybe we should. Anyway, I suppose that's right. As long as they work together, but it's always funny to me where the complexity lies and how we don't necessarily do justice to the other parts of the system. But that's getting more prevalent, is this soil structural interaction in these PBD processes, right? How much do we model of that behavior? And I think it's getting more common to model more of that.
Yeah, thinking back the last 10 or so years, I think it's going to become a risk item too, because of how many tall buildings and just in the United States have issues with foundations and leaning. And, there's the building in California and one in New York that are sitting empty and have leaned quite a bit. And it's, maybe foundations aren't the right place to innovate right now. So we don't need to go into that depth of that, but okay, so last question I wanted to ask that kind of goes over and summarizes all this, or maybe not summarizes it, but how many skyscrapers in your experience are designed and never built?
I actually had really good luck with mine. So if I can count, I would say Skyers Miami wasn't built, but that's the only one of my high-rise projects that didn't get built. So I think that 1, 2, 3, 4, 5 or 6 others did in my tenure, and then I worked on some other projects. But yeah, in my experience, I had great luck with getting buildings built. So again, I think it depends on the jurisdiction, how well does the building code official work with the team, right? Is it a significant issue for going outside the code, or are they really approachable on that? And then, I mean, honestly, all the projects that have, for me, gone on hold or gone canceled were financial. So
Yeah.
is the financial of the project safe, or is it, significant, robust? And if it is, then it's probably gonna succeed. So that's been my experience with that. Now, I think as far as the mega talls, that's a very different story. And I have not worked on any of the mega talls, right? I think those are like over 1,500 feet or something like that. I think that can be a little bit that definitely skews the number. I think a lot of those start to get designed and then don't get built. But just our average talls, I think have a pretty good track record if you're working with the right people. Yeah.
Okay. And then I always like to ask, is there any questions we haven't asked that you think our listeners would think is interesting, or any thoughts on tall buildings, or really anything that comes to mind? Really putting you on the spot here.
Yeah. I mean, I think I just want to reiterate my earlier comment that the people are more important than the projects. And as cool as it is to work on the tall buildings, it's way better to work with people that you want to work with. So in the grand scheme of a structural engineering career, if you have good teams, you're going to have good projects, and you're going to have a rewarding career, even if you're not working on the talls or super talls. So I think that's probably my closing statement. They are really cool, and there's a lot of fun things you do with them, but they're not the end all be all of structural engineering if you're working with good people.
Well, perfect. Well, thank you, Jordan, so much for joining us this week on the
This was
podcast,
fun.
and it was good having you back.
Yeah, thank you so much.